Um, okay, I hope you can see the full screen right now.
Yes.
Yes.
Okay, great. So my talk is dedicated to the search for the Millicharged particle, in particular the double hit signature in the brand new neutrino detector that we're developing right now. So this work was done by the group that I'm glad to present. Okay, so in the talk I will briefly overview the phenomenology of the Millicharged particle, what is the theory behind it, and why we are looking for it. And then I will go through the design of this new 3D neutrino detector we are studying, because our study is concentrated on that particular detector. And then I will go to the results of our sensitivity studies and the perspective we found for the look for the these MCP particles. So first of all, what is the MCP? The Millicharged particle are the class of the hypothetical particles that are carrying the fractional charge. The usual value is at the level of 10 to minus 3, comparing to the well-known electronic charge. It appears through the loop diagrams, and it was studied for a while ago. For example, the first look was done, I think, by Okun in 1984. So this is the extension of the standard model that could explain some phenomena that are still uncovered by the standard model. For example, it could be the possible contribution to the dark matter sector, or it could implement some additional symmetries at the high energy scale. So I put a few references that describes these prospects of such a theory with these hypothetical particles. It is expected that neutrino experiments, in particular accelerator neutrino experiments, are quite good in terms of sensitivity towards the MCP detection, because there is the large meson flux, and we expect these millicharged particles to be produced in the meson flux. So I will describe it on the next slide. So in particular, in our study, I will cover the context of the T2K neutrino experiment and the brand new scintillator detector we are developing. And I will prove so that it has a good performance towards the MCP search. So first of all, how the MCP could be produced. So the MCP, that is usually notated as high, could be characterized with its mass and effective charge. We have no direct hint towards its mass, while for the effective charge, we know that it should be at the level of 10 to minus 3 or 10 to minus 4 comparing to the electric charge. But for the mass, we have no direct hint. How we can find it? So we have a scalar meson that could decay into such a hypothetical particles. For example, for scalar meson, we expect to go them through the 3-body decay. So the diagram for this decay is presented on the right. And for example, for the pi 0, we expect it to decay into the photon and the pair of the high and anti-high, and the similar mode for the eta meson, eta prime, and so on. On the other side, we have also vector mesons such as rho, omega, and phi that could also decay through 3-body channel, but in addition to this particular channel, they can decay also through the 2-body decay channel directly into the pair of the high and anti-high. So I will show the diagram on the next slide. So for the 3-body decays, the branching is described with a formula below. So it starts with the branching ratio of the usual decay into the standard model particles. So if this branching is high, we expect this mode to be a very prospective for the search of these hypothetical particles. Then it is scaled with the effective charge. And then we have the kinematics that depends on the mass of the products and the parent particles. This formula is the same for all the mesons for all the 3-body decay channels. So I will present the visualization a bit later. So as I mentioned above, vector meson could decay through the 2-body mode directly into high anti-high, and this branching ratio is a bit more simple. As before, it is proportional to the branching ratio to the usual standard model particles, for example, electron-positron pair, and it is scaled with the effective charge. So the diagram is quite straightforward for such a process. So comparing to these 2 modes of the possible productions, this 3-body decay mode is less probable because we have more particles in the final state. while in contrary, we expect more scalar mesons to be produced in the proton-target collision. So this is the regime of the accelerator neutrino experiments. So in our study, we will consider both modes, 2 and 3 body decay, and we will try to find the best approach for the search of the MCP. So here it is the visualization of the branching ratios of all the modes we are considering. You can see that we are taking into account lots of different mesons as the parent particles, pi zeros, eta prime, rho, omega, and phi, because we are using 30 GeV proton beams. So all the mesons that could be produced were studied. And we considered all the possible modes, like 2 body decays and 3 body decay modes. So from this plot, we found that the highest branching ratio is provided by phi meson. Unfortunately, it's the heaviest meson, and that's why we have a pretty small contributions from the phi meson in our beam. So we are mostly populated with the light mesons like pi zero, eta, and rho, while the phi will provide us the larger branch ratios. So what are the possible ways to detect the Millicharged particles? Because before I mentioned how they could be produced. Concerning the detections, there are 3 general ways how it could be done. The first method is the search for this small DDX deposition, for example, in the long scintillator bars. And we are collecting the DDX over the path. Thus, in the result, we will have a relatively large deposition. The other possible method is to look for the single delta electron production. For that, we will have a rather large background contribution because there are many processes that could provide a relatively small energy deposition in the detector. In our study, we will concentrate on the coincidence of the 2 delta electron production. And this method is quite good in terms of the sensitivity, because we could reconstruct the direction of the MCP, and that's how we can suppress the background a lot. So once again, I will mention a bit more in details slightly later. So various neutrino experiments already performed a similar study looking for the Millicharged particles, and their results are summarized on this figure. So basically, these are the constraints on the effective charge versus the mass of these hypothetical particles. So you can see that many of these experiments are actually neutrino experiments like LSND, mini-Buni, and also there are some sensitivities from Dune experiment and so on. So that means that the neutrino experiments are the nice place to look for such physics. Speaking about our context of study or our hardware, this is the T2K neutrino experiment, Takaitu-Kamioka long baseline experiment. The main goal of the experiment is the precise measurements of the neutrino oscillation parameters and to look for the CP violation in the neutrino oscillations. But in the context of the MCP search, we will concentrate on the near detector complex. So the main concept of the experiment is the usage of the 30 GeV proton beam from the JPAR accelerator. These protons hit the carbon target, and that's how various mesons are produced. So in our study, we will look precisely in the natural mesons because that's how we expect the MCP to be produced. And then these mesons decay into neutrino, and this neutrino beam is studied with the complex of the near detector and the far detector. So as I mentioned, we will look in the data from the near detector, and we will try to understand, is it possible to detect the Millicharged particles and to put the limits or on its existence, or to perform the search towards the MCP. This study was motivated by the upgrade of the near detector, because the current setup of the neutrino detector, the near detector, is not suitable with the search for the MCP. So you can see the scheme of the near detector. It is the magnetized complex detector that consists of the scintillator targets that are shown in green, the so-called fine-grained detectors, and the gaseous time projection chambers. Right now, these scintillator targets are not suitable for the MCP search, mainly because of the relatively high dark rate of the photosensors. So our study is concentrated on the upgraded configuration of the NEO detector, and it is scheduled to be installed in 2022. We still hope that this is the reasonable schedule, disregard all the circumstances. And the main detector we will concentrate on is the so-called highly segmented scintillator active target. This is the brand new detector, and we are pioneering in its development. So there are some technical details concerning the upgrade. I just put the reference. So we want to prove that this geometry, this detector style is very powerful in terms of search for the MCP. So here you can see the overall scheme of this new detector that is under the development. The general idea is to build the solid target made from the 1 by 1 by 1 centimeter scintillator cubes. Each cube is read out with 3 wavelength shifting fibers that are inserted in the orthogonal direction. Thus, we have actually 3D reconstruction, because we are reading the signal from 3 surfaces of such a detector, and we can perform the 3D reconstruction. So the dimensions of such a detector is nearly 2 by 2 meters, and with a 60 centimeter height, and the total mass is about 2 tons. So in total, we will have about 2 million cubes and 60,000 channels. So here you can see some photos of the prototype of such a detector that was tested with the test beams, and the example of the event display. It's not from the expected MCP topology. It was obtained from the photon conversion, but just to illustrate the granularity of such a detector and what exactly events we will see from such a detector. So the main benefits of this detector is the fine granularity. As I mentioned, it's the level of 1 centimeter. Relatively low energy threshold. We expect 40 photoelectrons per channel for minimum ionizing particle, for example, for muon. So it will give us about 120 photoelectrons per 1 cube, because we have 3 channels per cube. And this is quite important for the MCP search, because the energy deposition is scaled with this effective charge. Thus, we expect a relatively low energy deposition. For this detector, we will use the MPPC with the low dark rate. Thus, we will have a severely suppressed background. And as we are looking for some exotics models, it's quite important. And we'll have the good time resolution at the level of 1 nanosecond. So all these characteristics were already proved with the various beam tests. Concerning the future of the T2K, we are going to collect the statistics at the level of 20 times 10 to 21 protons on target. That is the usual metric for the accelerator statistics by 2027. And one half of 10 to 22 PUT will be collected with this new detector I just presented. The good news for this study is that afterwards, the T2K will be replaced with the Tokai to hypercomiacande experiments. So the far detector supercomiacande will be replaced with the more advanced and the better and the bigger hypercomiacande setup. But for us, what is very important is that the accelerator and the near detector complex will stay the same. So we can continue our study with the larger statistics with the same setup we studied in our work. So in total, we expect to accumulate the statistics at the level of 2.7 times 10 to 22 PUT. So going to the particular T2K conditions and our sensitivity studies. We started with the estimations of the meson outcome from the proton collisions at the T2K target. We know that the common approach for such a study is to use the Pythia as the very wide use generator. Unfortunately, for our case, we cannot directly apply this method because 30 GeV proton beam is below the validated kinematics region of Pythia. So it's not so robust in our regime. And the second problem we faced is the the fact that the secondary interactions are omitted usually when we are using the PTA. So we found that it's quite critical to consider the secondary interactions of meson and to take into account all the produced neutral particles. So that's how we moved to GN4. And we consider the geometry of the T2K target. This is the carbon cylinder that is nearly 1 meter long. We performed the study of the various physics lists, and we tried to meet the agreement with the production of the charged mesons. So we found some particular list that was sufficient for this goal. We know this is not obligatory robust sign that we estimated the meson outcome in the most precise way. But the problem we faced is that there are no precise measurements of the neutral meson production at this energy region. So we can validate our model only with the charged meson production. That's what we did. So for the outcome, we estimated the meson multiplicity per proton collision, and as expected, we are dominated by the pi zeros with a bit smaller contribution from the eta meson, some contribution from eta prime, rho, omega, and a very small contribution of phi. But we should keep in mind that the branching ratios of the meson decay tells us that phi will much more probably decay into MCP. So we will continue to study all the possible mesons and all the possible channels. So these are the kinematic distribution of the produced mesons. And what is quite a good result for us is the good observation is that they are they have a relatively large momentum. So you can see that they're mostly above a few GeV, and that means that they will provide a boost for the daughter MCP particle. That's how the geometrical acceptance will be increased. So once we have the production of once we simulate the production of the MCP, we estimated the detector effect. So how the MCP could be detected in our detector. So here it is the scheme of the cubic structure of this SUPERFGD detector. So these are 1 centimeter cubes. And we have the neutrino beam that is coming from the left, and we expect to have some contribution from the high in this beam. And what we are looking at is the 2 delta electrons that provide us some light in the separated cubes. So this is the signature we are trying to detect in our setup. So to estimate how often this topology will happen, we can start with the estimation of the free path of the MCP in the matter, and it will be scaled with the effective charge, and it will depend on the energy threshold we are able to detect. That's why the low energy threshold of the SUPERFGD could give a benefit for our study. So taking into account the material of the SUPERFGD, this is mostly carbon. We estimated the mean free path of the MCP. But for our study, for our method, we want to detect the coincidence of the 2 hits. This is important because that's how the direction of the high could be reconstructed. And with this direction, we can severely suppress the backgrounds because the coincidence of the 2 hits is not so rare because, for example, we can have the noise in the cube above and below and so on. But once we reconstruct the direction, we select only events that are pointed towards the target. And that's how the background is severely suppressed. So this is the estimation of the probability to have 2 coincidence hits inside the SUPERFGD. So basically it depends on the detector length, on the detector efficiency, and the MCP free path that I described on the previous slides. Concerning the threshold, we estimated our energy threshold at the level of 1.5 photoelectrons that was driven by the various beam tests. And for the energy units, it will give us about 100 keV. So that is a relatively low threshold. And with such a threshold, we expect to reach the detector efficiency at the level of 92%. That is quite high. Once we we discussed the method of the detection. We performed the full chain of the simulation. So as I mentioned, we started with the simulation of the meson production, and then we simulate the production of the MCP that was obtained from the meson decay. And then we studied the geometrical acceptance of our detector. So the near detector in the T2K experiment is the slightly off axis to gain the sensitivity towards neutrino oscillation parameters, but it nearly has no effect on our study. The main limitations comes from the surface, the front surface of the detector. So it is 56 by 196 centimeters, and this is the basically this defines the acceptance, the geometrical acceptance of our detector. And the detector is placed in 280 meters from the target, and based on these numbers, we can estimate the geometrical acceptance. Good for us that most of the MCP are boosted towards the beam direction, towards the detector, and that's how we gain a little bit the geometrical acceptance. So you can see that.
Sergey, you have 5 minutes.
Okay, sure. Yeah, I'm approaching the final slides. And that's how we obtained the geometrical acceptance for different parent mesons. Once we are done with the full simulation chain, we can go directly to the expected sensitivities in our experiment. So first of all, let me briefly overview the possible backgrounds that we can face in our analysis. The first one is the MPPC dark rate. And we performed the estimation based on the known dark rate, the level of 0.5 kilohertz. And we found that the probability of this coincidence of two hits that are pointed towards targets is quite small. So if we use the two fibers from the cube to detect this hit, we expect a very small number of hits, the level of 10 to minus 2, that are originated from the dark rate. If we can use all fibers from the cube, then the total number of background events is nearly negligible, 10 to minus 4. These numbers are provided for the whole T2 hyper-K statistics. It's 2.7 times 10 to 22 POT. The other possible source of the backgrounds is neutrino interactions from interactions of active neutrino through the charge current. And for that events, we expect a relatively large track. Once again, it could be very easily suppressed by the cut sequence. We still expect some low energy backgrounds, probably neutron backgrounds and so on, but these should be studied more carefully during the data taking because there are not so many robust generators that could provide a good descriptions. There are not so many good models that could describe the interactions at the low energy from both neutrino or neutrons and so on. So in general, we suggested that our study will be background free. And based on the number of predicted events, we can estimate the sensitivity based on the expectation of 3 events. So here you can see the sensitivity of the T2 hyper-K experiment for different parent mesons. Here you can see that in the different mass region of the MCP, we expect a different meson to dominate. For example, the high mass region, we expect to have a main impact from the phi meson, while for the lower mass, we expect to have impact from the pi 0 and eta meson and so on. This is understood with the relative branching ratios and the kinematics factor. So comparing our results to others experiments, here it is the general plot. And the main conclusion is that the T2K and T2 hyper-K are very powerful towards this search. And this particular detector called SUPERFGD, made from cubes, is quite sensitive towards the MCP search. It has many benefits. And here we can see that we can overcome the existing limits in the relatively wide mass range from 100 of MeV up to 500 MeV. And with the additional statistics from T2 hyper-K, we will even extend a little bit this limitation. Okay, that's all from my side.
Thank you for your talk. We have time for questions. I think we can just unmute and ask.
Yeah, I have a question.
Yes, go ahead.
Have your group estimated whether the fire detector can be used as a to the advantage. Meaning that, of course, the fluxes are much lower, but you can use a single hit. And you could use the fact that it's going to be out of time because with the main beam, because the distance is far out. So I wonder.
Yeah, for the far detector, the main problem is the energy thresholds, because here we are speaking about the energy thresholds at the level of 100 keV, while the far detector, in our case, is the water Cherenkov detector. So it's nearly impossible to detect the particles at such energies.
Sure, but 5 MeV, this is what you can do. Right?
Yeah, I'm afraid if we will, for example, put the energy thresholds at the level of tens of MeV, we will have a nearly negligible probability to detect such the.
But you don't need the double collision on the other hand, and the size is much
yeah, sure, but well, I could not prove it right now, but well, I will do some estimations, but based on the very naive expectations, the water Cherenkov detector is not so suitable for such a search.
Well, you do detect neutrinos, right, over there, sourced by the same mesons, right? I understand that if it's a meson that is created in the beam dump and it's not collimated the same way by the horns and so on, then it's not advantageous. But if it's sourced by, say, kaons decaying to pi zeros in flight, right, and the pi zeros fragment further, and it's not obvious that you will not have events, right? And you can investigate a single hit out of time.
Yeah, may I say a few words?
Yeah, sure.
Yeah, I think it's a most serious problem in single search. It's double hit, single hit. It's a background, neutrino background, neutral currents, and scattering on electron. Of course, it could be studied,
but if your masses allows, I do not know. I haven't checked this. Right, this will be trailing all the neutrino background in time. Because if neutrinos are massless and they travel with the speed of light, and these guys are not traveling with the speed of light. So yeah, the near detector, it doesn't matter, but for the far detector, it kind of does.
Yeah,
but we also have some atmospheric neutrinos as well.
Yeah, I mean all neutrinos, not only beam neutrinos is less.
Well, the rate in super K is not that huge, right? It's still a pulsed beam, right?
Yeah, it's pulse beam. We use timing to suppress background, and we use time structure. But in case of big delay, we have to look at very low threshold, few MeV. And in our study, we use 200 or 50, depends about 100, our normal threshold for our neutrinos from J-Park beam. It's very high threshold.
Okay. No.
Yeah, but anyway, I think, yeah, your comment is right. For study or for search for sterile neutrinos, we use this excitation of oxygen to measure neutral currents and to put some limit on sterile neutrinos. But anyway, I think it could be, yeah, it could be studied. Yeah. Thank you very much. It's a good comment.
I have a curiosity, Yuri, since you are here. Which is the resolution you have on the direction?
Oh, well, basically, it is defined by the granularity of the detector. So we have the 2-meter long detector that is granular with a 1 centimeter. So, and the
no, but on the impact parameter. So how well you point back to target?
So it is 280 meters away. So this is basically 1 centimeter, because that's the step of the granularity, 1 centimeter divided by 280 meters. So that's the resolution, the angular resolution.
Okay, you don't have a plot showing, okay. Maybe with some simulation you can.
So, yeah, basically we have uncertainty within the given cube. So this is 1 centimeter over 200 meters.
Yes, I see, yeah.
Okay, I suggest we go to the next talk. Thanks, Sergey, again.
Thank you.
Thank you.